Hello, this video is for Stat360 handout number 10. The dataset that we'll be using for handout 10 is the T-scores dataset, which is available in our Google folder. So handout 10 covers additional tests of significance, and in particular it covers what we call the Big F test, which is a very universal and powerful test that is used to compare two regression models against one another. So this is a common test that is done. So we're going to consider bone density data. Bone density is measured by these quantities called T-scores. The wiki page here, I just pulled this information from the wiki page. So the wiki page for bone density, if you go down a little ways, they talk about T-scores. And these are just measures for screening for osteoporosis and then also osteopenia. They give us some guidelines for these scores. So if your T-score is of -1 or higher, then your bone density is normal. If it's below a -2.5, that's osteoporosis range. And then if you're between those two, you're in an osteopenia range. Okay. So here, this study is looking at how correlated or what is the relationship between spine T-score and forearm T-score. So spine, hip, and neck are kind of the gold standards when measuring bone density. And this client was interested in whether or not forearm T-score could be used as a substitute for spine and hip and neck for that matter. But here we're just going to look at forearm to spine. The idea was that the forearm T-score was easier to measure and cheaper than the spine T-score. So here's my regression model. Again, just modeling to see if spine can be used to predict the forearm T-score. Constant variance. Here's my regression model. The residuals look okay. I have random scatter above and below. I don't have problems with constant variance. Here's my regression output. R-squared of about 50%. Here's my coefficients down here. So we're going to dive a little bit deeper into that overall F test. That overall F test is given underneath the analysis of variance. Now what we have been doing is just verifying that that p-value there is less than 0.05. And what that means, if it is that we are 95% certain that a linear relationship exists between these two variables. In other words, it's relevant or important to consider the relationship between spine and forearm T-score on this graph. That line there is not going to be flat, is essentially what that's saying. Not just for this data, but if I were to go get another set of data, okay, and look at that line, I know, or I'm 95% confident that that line is not going to be flat. That's what that test is telling me there. Now, let's look a little bit more carefully about what this test is looking at. So the F test that we did up above here, so it's the overall one that's done underneath the analysis of variance, is very common and standard in regression output. The purpose of this test is to determine whether or not the regression model using the predictor specified is useful in reducing the unexplained variation. The two models that are actually being fit there have the following form. The H0 is that the expected forearm score or measure is just constant and does not depend on spine. The HA for that test can be written and looked at like this, which is that I do indeed need a regression model to explain the relationship between spine and forearm. So H0 here is indicating no relationship between those two, between spine and forearm, because spine is missing from this equation. But HA is saying that I can use spine to better understand forearm. So how would I get, or how would I model these models under H0 and HA? Well, under H0, that's simply going to be the mean. So the best estimate for beta 0 is going to be beta 0 hat, and that's just going to be the average T-score of everybody in the data set. And I guess that number's around 0.36 here. I can compute the sums of square error from this model, which is just going to be all of those distances from the points to the line squared and then added up across all of the data. And when I do that, I'm going to get 30.498. So this is going to be the sums of squares error for this model, for the model under H0. Now we're much more familiar with the sums of squares error under our regression model. I can get that by just looking at my ANOVA table and looking up sums of squares error. So earlier in the semester, we talked a lot about trying to get that quantity. Again, that's just the distance between the line and the points squared added up across all points. So these two quantities can actually be used to compute that test up above, or those quantities are being used to compute that test. So let's look at the F ratio for this test. And again, I'm doing it kind of in a general way. So this is the F ratio that we're going to be using for the big F test. What I have here is just the sums of squares error under the H0 minus the sums of squares error under HA. So all that is going to be the difference here between the 30.498 and the 15.591. So this is the sums of square error under H0. And this 15.591 is the sums of square under HA. So I would take 30.498, subtract 15.591. That's going to be what's in the numerator of that test there. And then I need to take a difference in the degrees of freedom between those. Now in this model right here, there's going to be 1 degree of freedom used because I'm actually estimating just one parameter here. So there's 1 degree of freedom that's being used in that model. Over here, I have 2 estimates that are being used, a beta 0 and a beta 1. So this is going to have 2 degrees of freedom here. So the numerator there, 2 minus 1 is going to be, excuse me, the degrees of freedom under H0 for the error term is going to be 40 minus 1 for this side. So I have 40 observations and I'm using 1 parameter. So that's going to be 39. And on this side, I'm going to have 38. So 40 minus the 2. So I need to be talking about the error term, not the model or the regression model. So the degrees of freedom for the error on this side is going to be 39. The degrees of freedom on this side for HA is going to be 38. Leaves me with a difference of 1 there. So let's just look at those calculations here. 30.498 minus the 15.591, and then I got 39 minus 38 here. In the denominator of this test statistic, I am simply using just the information from the right-hand side. The sums of square error under HA and the degrees of freedom for that error term on this side. So that's going to be 15.591 divided by 38 there. So this F ratio right here is what is done in this table. So now let's look at the information on page 6 there. So this here, 30.498, that is going to be the sums of square error from a straight line model, from just a line, a mean. That's what we had up above, minus the 15.591. So this numerator is actually just the sums of squares for the model, and then the degrees of freedom for the model. And then in the bottom, I have 15.591 divided by 38, and that's going to give me 0.410. I take the numerator, which is 14.9, divided by the denominator, which is 0.4, and I end up with this 36.33. So this big F test here, or this F ratio quantity, just shows you what's going on with this overall F test. And the structure of my analysis of variance table, okay, how we set that up is just so that we can conduct that overall test. From this, we can get our p-value. We just need to know that it's coming from an F distribution. The degrees of freedom for the numerator of this statistic is 1. The degrees of freedom for the denominator of this statistic is 38. So when you talk about an F distribution, they're going to talk about what is the degrees of freedom for the numerator and what is the degrees of freedom for the denominator. So those are going to be 1 and 38 here for this example. You can get this p-value, okay, from the online apps here, or you can get that in R if you want. Of course, JUMP automatically computes that for us, so we don't have to worry about that here in this standard test. Okay, so let's extend beyond the standard test. So what that overall F-test really allows us to do is to compare two models against one another. Okay, the two models that I was interested in were just a mean model and then a regression model, the estimated regression model. But this test, that overall test, can easily be generalized. Okay, so I can test any two models against one another. Now, one model has to be a subset of the other, but we'll talk about that in a minute. So the overall F-test simply tests a flatline model against a regression model. But what we're saying here is that I can use, this doesn't have to be a flatline model. This could be any model that I'd like to test, and this would be another model that I'd like to test. So I can actually use the big F test, which is, again, very similar to the overall test that's done by the regression. I'm just going to be using a substitute here instead of this flatline model. And that's going to allow me to compare two different models to one another. And we affectionately call this test the big F test because it uses the F distribution. It's the big F test because it's quite powerful and can be used in a large variety of situations. So let's consider our t-score investigation here. We wanted to determine whether or not the forearm could be used as a substitute for the gold standard spine t-score. So here the orange line in here, or tan line there, is the y equal x line. And then the other one is the estimated regression line. So if I want to test whether or not the estimated regression line is close enough to the y equal x line, so if the estimated regression line is close enough to the y equal x line, I could use forearm t-score as a substitute for spine. However, if these two lines differ statistically enough from one another, I shouldn't do that. So a test of agreement here is just going to try to verify whether or not my regression line is close enough to the y equal x line. In the context of this problem, the y equal x line just means that the forearm, the expected forearm score, will just be the spine score. So that's the line of agreement there, or the y equal x line. Y is forearm here, spine is x. So this is just an agreement. HA is that they don't agree and I need to use some other form for my regression line. If I want to write these out with the coefficients, with the parameter estimates here, the beta 0 would be 0 in this model and the beta 1 would be 1. The model under H0 is often referred to as the restricted model. So this model right here is restricted in a sense. It is restricted in the sense that I am specifying the y-intercept to be 0 and the slope to be 1. The model in the HA is often what's called the unrestricted model. In HA, we usually just have these parameters here. There's no restriction to those, so we often call that model the unrestricted model. Now the restricted model, okay, the model under the H0, must be a subset of the unrestricted model. So this F-test requires that the model under H0 is a subset of the model under HA. So for example, I can't be doing a test like the following here, where I'm interested in H0, the expected neck score as a function of spine, and then HA, the expected forearm score as a function of spine. These two models here are not nested, or the H0 is not a subset of the model under HA. Okay, so this test right here could not be done with the big F test. Again, because this H0 model is not a subset of the HA model. Okay, so how do I get these models in JUMP? So I have model 1, which is the restricted model. And that is just going to be that the expected forearm is equal to the spine. In other words, that's the y equal x line. And then the unrestricted model is just going to be my regression model. So we already know how to fit the regression model. The error term for my sums of square error, that I'm going to be using in that big F test is again that 15.591. That's based on 38 degrees of freedom. So I can get this model here, the restricted model, and this again is going to have the y-intercept be 0 and the slope be 1. I can get that fit. I'll show you how to do that quick. Over here under Analyze, I want to select Fit Y by X. I am looking at the forearm t-score as a function of the spine t-score. Go ahead and click OK. And then from my drop-down menu here, I can say Fit Special. Zoom in for you there. Say Fit Special here. And then here I want to constrain the intercept to be 0 and the slope to be 1. So in my Fit Special window, I want to constrain the intercept to be 0 and the slope to be 1 and say OK. And what I get here is my line. This has us y-intercept 0, slope 1. And then down here under my sums of squares, I'm getting my sums of squares for this model. 40 is my degrees of freedom, and 24.85 is my sums of squares. And that's what's provided here on page 10. 40 is my degrees of freedom here is because I am not estimating any parameters. I am forcing the slope to be 1 and the y-intercept to be 0. So I retain all 40 of my observations for my calculation of my error term. So this model for the numerator, what I'm going to be doing is just taking 24.85, subtracting the sums of squares from my unrestricted model, which is 15.59. And then divide that by 40 minus 38. So here I'm doing top of page 11, 24.85 minus the 15.59, 20 minus 48. So this is going to have degrees of freedom in the numerator 2. And then my error term or my denominator is still going to be the same. So this denominator here is always coming from your unrestricted model and the degrees of freedom associated with that model. So when I do all that math, I get 11.28. I need to figure out whether or not that's extreme against an F distribution with 2 and 38 degrees of freedom. And the p-value here is 0.0014, which is going to be less than 0.05. So in other words, I have enough evidence to reject the H-naught. The H-naught is wrong. I believe the HA. And the HA says that I need something other than a y-intercept 0 and a slope 1. So that means I don't have agreement between my spine and forearm. So conclusion here, we are 95% confident that a linear relationship that exists between those two is different from the y equal x line. That's a typo there. Should be y equal x line. More practically speaking, we are certain that there is not a one-to-one match between these two types of measurements for bone density. So I cannot use spine as I cannot use forearm t-score as a substitute for spine. On page 11 and 12 here, or 12 and 13, I give you how this test can be set up with matrices. So under H-naught here, that's what this would look like. And then under HA. That numerator calculation there, that sums of squares from under H-naught minus under HA, can be done with the following expression of matrices. This cap C here is just the coefficient on your parameters. The little c here is just the little vector that you want those set to. So I want my slope set to 0 here and my y-intercept set to 0, my slope set to 1. So that's why I have it specified as 0, 1 here. We're going to need to know how this is set up in order to set this up in JUMP as well. So JUMP kind of uses this same structure. Here's the calculations in R, getting the p-value. Page 13, let's show you how to get this done in JUMP. So what I need to do inside of JUMP from my drop-down menu is select Estimates, Custom Test. This menu, or this custom test window, is going to pop up here. So let's go ahead and do that, and then I'll show you how to put those coefficients in there. So from my drop down here, oops, I need to go under Fit Model to do this. So forearm, spine, select Run. Estimates, Custom Test. So Estimates, Custom Test here. Down towards the bottom, we're going to maybe pull that up to the center of the screen a little bit. I can give my test a name here. So we're testing the y-intercept equals 0 and slope equal 1. I'm testing two quantities here, so I'm going to need to add a column. This first column is going to be for the y-intercept. So I want to put a coefficient of 1 on that, and I want that y-intercept to be 0 here. So the row just picks up the coefficient, and then I have the equal sign to 0 here. I also want to test whether or not the slope is equal to 1. So here I want to pick up the coefficient for the slope. So I want to put a 1 in that row, and I want to know whether or not that's equal to 1. I got this second column here by saying add column. So once you get that specified, I'm going to say done here. These top two rows and top columns here are the capital C matrix. And these two right here are the little c. So that one and that one here are the little c. That's a vector of 0, 1. Okay, go ahead and click Done. And then what that's going to do is produce the output that I have here on page 14. Inside of that box there is the information that I'm going to use. The test statistic here is at F ratio value, 11.28. That's exactly the same number that we computed up above. And the probability associated with that is the 0.001. You can see that my numerator degrees of freedom here is 2. That is coming from that would be the 40 minus the 38 here in this case. So all I really need here is that p-value, the prob bigger than f, inside of that box. This here is doing that p-value right there is for this custom test that we created, which is up here. Looking at whether or not the regression line is close enough to the line of agreement. Okay, there's some tasks here at the bottom of this, page 14. If you want to just kind of work through those, that'll get you accustomed to creating these things and then putting them into practice a little bit. So for which type of test or t-score coming from spine, hip, or neck, which one does the forearm tend to agree with most? Okay, that does it for handout number 10 for Stat 360. Thank you.